All right, yeah, so I'll make a start. So thanks to Christina and to Sums for having me speak at the seminar series. And thanks for putting up with me bailing last week and delaying it till today. And thanks for coming along today. Yeah, so my name's Nathan Brownlowe. I teach 1902 first semesters, been doing that for quite a while, and measure theory in second semester. So hello, if I don't know you. I know some people, I don't know if I know everyone. So what I want to talk today, what I want to talk about is basically quantum groups. And I'm talking about these things because it's only really recently that I've learned what these things are about and have become quite interested in them. I'm going to talk today about compact quantum groups, or a type of quantum groups that's a sort of big part of the wider field of quantum groups, which is really quite big, has two basic approaches. There's a purely algebraic approach to these things, and then an operator algebraic approach, so there's some analysis involved, and that's the side that I work on. So there'll be some like analysis type things floating around, but they won't play a big role today. So I've been working in and around these things for basically ever since I've done the PhD, but I just never learned what they were. So I've been to plenty of talks about them and just ignored them, or in one ear, out the other. I just didn't know the basics. And a friend of mine from New England and I sort of asked ourselves a natural question about them, and that was the thing that we needed to actually learn these things, and we put a paper on arXiv last month. So now I'm really interested in them and still learning, very much still learning. I have three goals for today. First goal, first half of the talk, tell you what a compact quantum group is in all its glory, the whole definition. And then the second half of the talk is an example, which is quantum symmetric group, which is these quantum permutations, right? So it's really just an example of a compact quantum group. The third goal is, well, this talk's really mathsy because I don't know how to write talks that aren't like super mathsy. I mean, I can't hide all the maths under the rug and just have pretty slides and pictures and stuff. I just don't do that. I can't do that. So I'd rather put all the maths on there and then tell you, okay, just ignore that bit. Don't worry about that bit. That word, forget about it. So that's how I approach these things. So my third goal is to sort of show you, especially if you're in first year, that okay, there might be a bunch of things that you don't know yet, you haven't seen, but you're only like a few classes away maybe to understanding all the things you need, right? So you're getting there. You can see it in the not too distant future. We'll see if I'm successful at that. If you just think like that was just a confusing mess, please tell me like that was just crap. We'll see how successful I am. Okay. All right. So let's get started. Remember, the first half of the goal is to get to the definition of a compact quantum group. Okay. All right. So immediately, there's fancy words, and maybe especially if you're in first year, you just haven't seen these words yet, right? Don't worry about them. So let X be a compact Hausdorff space. These are topological words. It's a nice space. You should be thinking about one or more of these examples. So a finite set is such a space. Maybe the thing to think about is a finite, like a bounded interval, right, in the real line, A to B, right? If you're in 1902, we did an assignment, continuous functions on -1 to 1. So just think about that, -1 to 1. Closed bounded subset of a metric space, if you've seen those words, okay? So these are the spaces I want to talk about. It's just a nice set of spaces, think closed bounded interval. As the title suggests, I want to really think about the functions on them now. And I want to look at continuous functions from this space to the complex numbers. Right? The field for me is always complex numbers, right? So our number system, always complex numbers. This set of functions has a lot of structure on it, and it turns into what's called a normed star algebra. So there's three things here. It's an algebra, it's a star algebra, there's this star thing around, and it's normed, it's got this norm on it, right? So what do I mean? So the algebra, think vector space, so scaling and adding, and then think an extra operation, we usually write it as a product, but it's just this extra operation that interacts nicely with the first, like with the vector space operations. And everything is pointwise here, right? So we scale functions pointwise, we add functions pointwise, and we can multiply functions pointwise. So it's all very nice and natural. These operations turn this thing into an algebra over the complex numbers. There's this star thing around as well. Think sort of transpose. I'll mention the matrices in a second. Think sort of like a transposey type thing. But for here, you just take complex conjugate for what you get, right? This satisfies what you need for like what's called an involution. And this norm, a norm is a length function. So like in 1902, we quickly talk about a length of vectors. When you generalize this to sort of things that aren't just Rn, we call it a norm, right? But think length. And if you take the supremum of the maximum, like of the biggest that gets in absolute value, the function values, this thing turns into a length function, right? It satisfies what you want out of a length. So the continuous functions on a nice space is what's called a norm star algebra. It has all this structure. Actually, there's more structure, and it is an example of what's called a C-star algebra. So the field of C-star algebras is basically where I do all my work, or almost all of it. And like, you know, ever since my honours, really. And as we'll see, quantum groups involve C-star algebras, and even though that's the case, I really didn't know anything about quantum groups for a very long time, until a year or two ago. Okay, so what is the C-star algebra? I will define it, although I'll basically be like, just ignore most of this, but some examples. So we've all seen examples of C-star algebras. The complex numbers is a C-star algebra. It's like the trivial one. The n by n matrices with complex entries is an example of a C-star algebra. Bumping up to infinite dimensions, if you've done, you know, some analysis in second, third year, if you take a Hilbert space and take bounded linear operators, these are somewhat like infinite matrices. This is an example of a Hilbert space and of a C-star algebra. And as I said, continuous functions on a nice compact Hausdorff space X is an example of a C-star algebra. It's a commutative one. I didn't mention that on the previous slide, but when you take the product pointwise, FG, that's the same as GF. Hopefully that's clear, right? So the functions commute. And in fact, it's a big theorem in the subject that all commutative C-star algebras look like C of X. So that's all they look like. So we'll be coming back to C of X. Let me put up the definition of a C-star algebra. Why has this died? So here it is. We don't have to worry about it too much. I just wanted to put details down. So it's a norm star algebra, like what we talked about in the previous slide. It's an algebra. There's this involution star. There's a norm around. We want it to satisfy some extra structure. So we want it complete under this norm. So like the real line is complete under the absolute value, like there's no holes in it. You take a sequence that converges, it's going to go to something that's a real number. Whereas like the rationals, you can get a sequence of rationals that approaches root 2. But root 2 is not in the rational, so there's like a hole where root 2 should be. So the rationals are not complete. The real line is complete, there are no holes, and this is the basic idea of being complete. So we need this thing to be complete. We need some algebraic stuff in the second dot point. So this is all about how the involution interacts with things. It's also quite natural. Think for the matrices, the involution is conjugate transpose. So if you picture like these A's and B's as being matrices and everywhere you see a star, it's conjugate transpose, you'll sort of, these are all believable things. And then we need this extra innocuous looking thing, it's called the C-star identity. It's how like the product and the adjoint, the involution and the norm all sort of interact. The norm of A star A is the norm of A squared. If you have that for all A, you have what's called, and you know, the rest, you have what's called a C-star algebra. Okay, these don't have to be commutative at all. As we know, matrix multiplication, well, as of Monday in 1902 at least, matrix multiplication is not commutative. If it is commutative, it turns out you're C of X. Okay, so back to C of X. Lots of fancy words on this thing, on this screen, on this slide. I'll read it and then say, don't worry about it. So thanks to some old Russian mathematician, I believe, we have this sentence. There is a categorical equivalence between the category of compact Hausdorff topological spaces and the category of unital commutative C-star algebras. Forget about that. Let's change that to, there is a strong mathematical connection between spaces like the ones I talked about, like finite sets or bounded intervals on the real line, and the functions on them. And like I said, in fact, I could change the continuous function c of x into just unital commutative C-star algebra. Don't worry about the unital, there's like an identity around. Forget about that word. But yeah, because every commutative C-star algebra looks like this, or as long as it's unital, there's this sort of way of transferring data back and forth between these nice spaces and commutative C-star algebras, right? So in some mathematical sense, some very precise sense, they're sort of equivalent. Okay, now, an important point, because I'll actually be doing calculations later, an important point is this equivalence is what's called contravariant. So, not only are the spaces and the functions on the spaces in some sense equivalent, but maps between them are as well. So if you take a function between two spaces, phi from x to y, this equivalence, this theorem, is also telling you information about how the maps come back and forth. And so a function from x to y actually gives rise very naturally to what's called a morphism from the functions on these spaces, but it flips direction, right? If phi goes from x to y, this phi star goes from c of y to c of x. And this is the formula, it's very natural. If you put in a function on c of y, you just compose with the original phi. So if you think about this equation, hopefully it's clear that phi star really goes from c of y to c of x. The word contravariant is this flipping, right? X to y suddenly is converting to cy to cx. Okay, so when was it? In the 80s and 90s, French mathematician Alain Connes, who was a Fields medalist for previous work, fancy guy, he came up, basically built the theory of non-commutative geometry. And the basic idea for non-commutative geometry is this theorem. There's this really strong connection between these spaces and functions, like commutative algebras. But there's this whole world of non-commutative C-star algebras, right? Plenty of examples, like even matrices, they're non-commutative. So if we want to introduce an idea of a non-commutative space or some sort of quantum space, and as you'll see, the word quantum really means non-commutative for me. So sorry if it comes across any fancier than that. Then, if you want to like quantify, that's an actual word, quantumize, whatever, something that's not a real word, the spaces, that's really non-commutative C-star algebras. Right, so if we want to introduce an idea, so if we want this picture in this quantum realm, which is really non-commutative land, the thing to study is non-commutative C-star algebras. Commutative C-star algebras will give you the classical spaces. If we study non-commutative C-star algebras, this is this analog of a quantum space. And quantum groups, at least the type that I look at from the sort of operator algebraic approach, fit into this framework, this non-commutative C-star algebra framework. Okay, so don't be surprised now when the definition of a quantum group involves a C-star algebra, like a general C-star algebra. Okay, so now suppose, now instead of an X, a space X, we have I'll call it a G, and it has some extra structure, it's a group. I have no idea how long this talk goes, let's hope that I'll kick myself off if I'm running late. Yeah, so suppose G, compact Hausdorff space, but it's also a group. If you're in first year, maybe you haven't seen this notion of a group. So I have definition of a group pretty quickly. It's very natural, but it's super important. I mean, if an alien came to Earth and you had to tell them about one mathematical object, I would tell them about a group. Right? I think it reigns supreme amongst all mathematical objects. This is the definition. It's quite simple, but super rich theory, group theory. People today just spend their lives coming up with really cool groups and group properties and stuff like that. So it's a set with an operation. I'm going to call it GH, just multiply, where it's associative. That's the first dot point. There's an identity element, right? I call it E. And then for hg, there is this inverse, h, that gets you back to E. Maybe you're thinking about a vector space, which is good. A vector space under addition is a group, where the identity element E is the 0 vector, and you've got these additive inverses, right? So we've all seen groups. That's the general definition. Instead of just writing the product as GH, I want to record that as a function. So my little m is multiplication. So I've got a function from G cross G to G. So m of GH is what I really mean by GH, right? It's the product. Okay. So associativity, which on the other side I jumped to, I wrote like this, which is the usual way you just write associativity. It doesn't matter which order you do the products. If I'm going to use this function notation, I can write associativity with a diagram that I insist commutes. So the curly arrow here just means this diagram commutes, which means, say, if you go across and then down, if you compose those maps, that has to be the same as going down and across. That's what I mean by commuting diagram. But this is exactly associativity, right? This m cross identity just multiplies in the first two components, and then you multiply again. So this is like right down is GH times K. And then here, this is multiplying in the second two components, and then multiply. So down then right is like the G times HK. Does that make sense? So this diagram, commuting, is exactly the same as saying this little thing here, right? Okay, now, I want to go to the functions on this basis, right? So I want to dualize this picture. So this is like my phi from x to y, right? This is my map M from space to space. I'm going to dualize this and get a map on functions, and it flips the order. So taking the dual of this multiplication gives what we call a co-multiplication. And now, instead of like m star, which is what the notation I would have used, right? I had phi and I wrote it as phi star. I'm going to write it as delta g. Delta g is exactly this map, that when you feed in a function, you just compose it with the original map, right? So delta g is now a function from the functions on g to the functions on 2 copies of g, given by this composition, okay? But I can dualize that whole diagram I had, right? So, and I get this. So I get another commuting diagram. This is all true. All this comes from the fact that, G is a group. This little m map is associative. So notice I'm sort of flipping the order of things. Classically, I went from 3 copies to G down to 1. But when I dual, I'm going from 1 copy of the functions down to 3 copies. And the maps on there are just dualizing the maps. I get these delta g's appearing. So that function delta g satisfies this. This diagram commutes. And then there's this other thing I've put on for completeness, and I'm going to completely ignore it. Technical thing. Some spans of things are dense inside the functions on G cross G. Completely ignore that. We get this extra bit of information at the bottom because G is a group. It's important because it appears in the definition of a compact quantum group. So it's there, but let's agree to ignore this. Technical stuff, who cares? Okay, I'm almost ready to present the definition of a compact quantum group. I just have to do one little technical thing. Because the idea, remember, is to replace my commutative algebra with something non-commutative. So that's going to become an A. But how do I replace this? I mean, it obviously sort of involves C of G, but it's not quite, right? Like, what do I do there? Okay, well, turns out that C of G cross G can be described as such. This is called a tensor product. Technical, somewhat annoying little thing. Just think of this as taking the functions on G, and putting them together somehow, right? But you're doing it in a way that this algebra is the same as just the functions on G cross G. Okay, so I can rewrite this all comes for free just from having a group, right? Because multiplication is associative. I get all of this, and so now I say, all right, this is, well, not me. as you'll see, Woronovich in 1987 said, this is the crucial information. If I take all of this and then I just ignore the fact that I have a commutative C-star algebra, what I have left is what I'll call a quantum group. And I use the word group because it comes from a group. This only happens because I have a group, not just a space X. I wouldn't get all this information. And so here it is. Here's the definition of compact quantum group. I now have a C-star algebra A. If it's commutative, it'll look like the previous example. It'll look like C of G for G group. But it doesn't have to be commutative. And a co-multiplication from A to A tensor A, that's like this map from C of G to C G cross G. And I want co-associativity. So I have to insist that this diagram commutes now. I don't get it for free because it comes from a group. I have to insist that I have this. And I have to insist that I have this technical thing at the bottom that we're going to ignore. Yeah, so if you come to me with a C-star algebra and a map from it to the tensor product of itself, and you can show me these things are true, like this commutes and this is true, then I'll say, great, you have a compact quantum group, right? So they're not groups, they're sort of much more complicated than groups. The term compact quantum group sounds like it's a type of group, it's not. It's really a C-star algebra with a co-multiplication. Okay. All right, so the rest of the talk is in a particular example, which is quantum symmetric group. There are lots of examples of compact quantum groups, but you know, this is a pretty full-on definition, right? There's a lot of sort of theory involved in this. So, you know, not easy to just come up with examples. One general way of coming up with an example is to take a classical group and try and quantumize it, right? So you take the group, you look at the functions on the group, and somehow try and lose commutativity and get something that we all agree, yeah, that's sensible enough to call the quantum version of that group, right? And this is the case for this example, this quantum symmetric group. Okay, so the symmetric group. Here's an example of a group, really important class of examples. So let X be finite, right? So just a finite set of points, we'll label them 1 to up to n. If you take a 1-to-1 and onto function from X to itself, we call that a permutation, right? You're just commuting the 1 to n. So this is called a permutation, and these form a group where you just compose functions. Right, this is called the symmetric group Sn. Right, so as n changes, you get, as n gets bigger, you get a bigger and bigger group, you get different symmetric groups. Right, so an example, so sigma 1 and sigma 2 are permutations, and we write them like this. So this is saying sigma 1 sends 1 to 1, 2 to 3, 3 to 2, and 4 to 4. That's what notation means. It's not a matrix. So sigma 1 is leaving 1 and 4 alone and just swapping 2 and 3, for instance. And sigma 2 does what it does. But we can compose these, right? And we compose from right to left. So if I write sigma 1, sigma 2, I do sigma 2 first and then sigma 1. So for instance, sigma 1 sends 1 to 2, and then sigma 1 sends 2 to 3. So the composition sends 1 to 3. Right? You just go through, compose, you get a new permutation. So is everyone right with that? It's an example of a group. I'm sure you can guess what the identity permutation is and what an inverse would be, right? Okay, so that's a group, and so now we ask, what's a quantum version of this group? Is there one? I now feel time pressure. Do people eat during the talks? Or?
No, just at the end.
Okay. All right. Okay. All right, let's go. So, how do we work out a quantum symmetric group? So the idea is to study the functions on the group, right? And what we're going to do is identify this nice family of functions in the functions on Sn, and that'll be the key to going quantum, right? I mean, none of this is obvious, right? People, fancy people wrote papers about this decades ago, but yeah, that's the general plan. All right. So now I'm up to the maths. So I want to actually do calculations. So bear with me. We'll see how fast we can get through it and get to the pizza. So I want to capture the action of Sn on x. The word action is a sort of fancy word, but basically, like, what does Sn do to x? Like, a permutation is a function on x, right? You evaluate these functions. I can capture this idea of evaluating a permutation on a function with this phi, right? So phi Sn cross x to x, you feed in a sigma k, so a permutation and a point. Phi is just telling you what sigma does to k, right? So it's just evaluating at the permutation. But I'm capturing this in one function, and then I want a dual. So now we take phi star, so now we go from the functions, and it's flipped, right? It's contravariants, and now I'm going from c of x to c of Sn cross x, which is this tensor. And again, it's just the same thing. Phi star of a function is f composed with phi, right?
What is the solar equal mean?
Sorry?
The solar equal sign. The big limit.
Yeah, this is like isomorphic. So these two things are the same thing. Yeah. Okay. All right. Now I want to feed in an actual function into phi star. So there's a very natural class of functions in C of x, just the point mass functions. So if I take my favorite point in x, I, pi is just going to be the function that's 1 at I and 0 off I, right? So what does phi star do to a pi, right? So pi of k, this is the Kronecker delta function. This is 1 when these match and 0 else. So delta, so pi at k just checks, is ki? If so, it's 1, otherwise 0. So let's check what this does, right? Phi star of pi, let's feed in a sigma k. What's phi star of pi? It's pi composed with phi. So pi composed with phi of sigma k. What's phi of sigma k? Well, that's really just implementing what sigma does. So I'm looking at pi of sigma k, and then that just checks, okay, is sigma k equal to I or not? If it is, it's 1. If it's not, it's 0. So phi star of pi at a sigma k is this Kronecker delta. Okay? So I'm going to make a claim now. And these fij's are these magic functions that, oh, shouldn't use the word magic, that's actually a technical word I'll use later. These special functions in C of Sn that'll give rise to the quantum stuff. So for I and j between 1 and n, so I and j are points in x, consider the function fij, it's a characteristic function, right, on the set of permutations that send j to I. So so these functions are in C of Sn. You feed in a permutation, and it just tells you does the second component subscript go to the first, right? If it does, then it's 1. If not, it's 0, right? So these are functions on permutations. I claim that phi star of pi, the function we considered previous slide, can be expressed in this form involving these fij's. Now, if you're wondering, hang on, this is a function, what's this? That's fair, right? Technical thing. I'll just explain in the calculation. Basically, when you feed in a sigma k, they act on coordinates and multiply. Okay, so let's do this calculation. Okay. So, to this thing, feed in a sigma k. Everything's linear, right? I don't work with stuff that's not linear. So you can just feed it right into the functions. And as I said, the way this little tensor works is you just feed in the components and multiply. So put the sigma into the fij's, put the k into the pj. So immediately, the pj will kill all the k's except for j. And then it's just 1. So this whole sum just collapses to one term, and I get fik of sigma. That should be yeah, no, that's fine. Right, the k's fixed. So the j will vary, and just when j's k, it locks on, gets you something, the rest get killed. So fik of sigma, and this is the formula, right? It's 1 if sigma of the second subscript is the first, so 1 if sigma k is I, 0 otherwise. But that's exactly what this, on the previous slide, phi star of pi did. Right? It evaluated as sigma k was exactly this Kronecker delta. So hopefully you now believe that if I take the action phi, joule, feed in one of these point mass functions, out pop these, not magic, but special functions, fij. Okay. What does the co-multiplication do to these things? Well, it does something quite natural. So co-multiplication from C of the group to C of 2 copies of the group. I claim that if you feed in an Fij, it is the sum of these functions where you're varying the inner subscripts. So let's do this. Left-hand side, feed in a sigma 1, sigma 2. Right? Remember, how is co-multiplication defined? It's the function composed with multiplication. Right? Little m, but I'm not carrying around the little m anymore. So delta of f at a pair is f of the product. Right? And Fij just checks, is this permutation at j equal to I? If so, it's 1. If not, it's 0. So that's what the left-hand side does to a sigma 1, sigma 2. And the right-hand side, remember that you feed in the 2 components and you just sum. So Fik of sigma 1, Fkj of sigma 2. So feed them into the functions and multiply. And now what happens? Well, each of these Fiks are Kronecker deltas, right? So the first one is checking is sigma 1 of ki. And the second one is checking is sigma 2 of jk. And if you stare at this long enough, you can convince yourself that this all collapses and just checks is sigma 1 of sigma 2 j equal to I. I.e. the same thing. Right? So I do in fact have this sort of what I think is very natural formula for co-multiplication on this special class of functions that I'm considering. Okay, so to summarize, and we're getting close to the end, just starting with the action of the symmetric group on X, right? Just evaluating permutations. I dualize, I feed in my point-based functions, like the standard basis elements, the most basic functions I have, and I discover these functions Fij. These functions satisfy a whole bunch of things, some of which are easy enough to sort of convince yourself of. Fij is Fij star is Fij squared. Well, these are Kronecker deltas, right? They're 1 or 0. So if you complex conjugate, that does nothing. If you square them, 1 squared is 1, 0 squared is 0. So these things satisfy the first dot point. It means they're called projections. The second dot point is not too bad. If you fix one of the subscripts and let the other one run, I claim that you get the identity function. Because, like, for instance, if you give me your favorite sigma, right, and I fix j here, then sigma of j is something. And as I run through that I, that I sums, I'm going to hit that something at some point and get 1, but all the other ones get killed. So no matter what sigma you give me, I'm just going to get 1 out of those sums. Does that make sense? So these sum to the identity. The third dot point is technical. The functions on Sn are generated by these functions, so it's crucial, but we're not going to get into it. And we saw I proved this nice formula for co-multiplication. So it turns out that these functions are what we need, and now we're going to go non-commutative. And so Wang in 98 came up with this theorem and claimed, that everyone agrees is the correct notion of quantum permutation group, or quantum symmetric group. So what you have to look for, instead of functions in a commutative C-star algebra, look for a family of elements in a C-star algebra that are projections that sum to 1 if you run one of the subscripts and fix the other. And he proved that there's a co-multiplication on this thing that satisfies exactly the same sort of formula that the functions did. he proved that this is a compact quantum group. And he said, this is what we should think of as quantum permutation group, and everyone's like, yeah, this makes sense. I mean, one way to see it makes sense is the abelianization of this thing, which is a technical thing, which basically just means make everything abelian. You get the functions on Sn, right? So that's the main reason why this is like, yeah, this is quantum Sn. So my last slide of content, I mentioned in my abstract, it turns out that there's only something interesting going on when n is bigger than or equal to 4. Interesting in terms of actual quantum stuff, actual non-commutativity. There's the word magic. That actually is a word. These aij's you can put into a square matrix, right? And their projections and the rows and columns sum to 1. This is the thing, we call it a magic matrix, right? If we were working in one-dimensional world, so these are either 0 or 1s, you'd have to have exactly 1, 1 in each row or column. These are called permutation matrices, right? And no coincidence. Anyway, in general, if they're just projections in some abstract C-star algebra, we call these matrices magic. All right, so if n equals 1, then this matrix just has the identity in it, and you just generate a C-star algebra, you get the complex numbers. So, boring, commutative. If n equals 2, we know exactly what the magic matrix has to look like. Okay, you're allowed some projection here, but if these have to sum to 1, then this has to be 1 minus it. And so does this column, right? This column sums to 1, so this has to be 1 minus it. And then the bottom right-hand corner is p as well. Everything here commutes. And so you just get a copy of C2. So not commutative, no quantum symmetries. n equals 3, much more complicated. But if you have a 3 by 3 magic matrix, it turns out all the entries must commute. But that's quite hard to see. So you get some commutative C-star algebra, nothing's non-commutative. If you go to n equals 4, the best way to see it is you've got enough room to get non-commutativity going in this sort of strong sense. If I just take the 2 by 2 grid here with my p, 1 minus p, and then the bottom 2 by 2 grid, I can have a q, 1 minus q. These p and q don't interact. If I sum rows and columns, I'm getting 1, and p and q aren't seeing each other. So the p and q can be chosen to be non-commuting, nothing to do with each other. And so when I generate the C-star algebra, whatever that means, I'm getting something. Oh, my mum's calling me. I'm getting something. Sorry, I'll just give up on that. I'm getting something non-commutative. Hopefully that's sort of believable, but this is all sort of technical stuff. So symmetric group on 4 or more points has quantum symmetry, like there's a quantum version. So there's the Wang paper. Woronovich wrote lots of papers on this stuff in the 80s and 90s. I think it's a really interesting topic. Yeah, sorry for all the maths, but thanks for coming and thanks for listening.